All right, let's get into it. You probably remember the periodic table from school, this beautiful, super orderly chart where everything follows these nice, neat trends. But what if I told you there's a whole chunk of that table that just loves to break the rules? A bunch of rebels that totally defy our expectations. Today, we're unlocking the secrets of those rebels, the D-block elements.
You know, this quote just nails it, right? These elements don't follow the simple patterns of getting bigger or smaller that we see everywhere else. They are the cool, kind of unpredictable characters in the story of chemistry. They're not so out there that they don't fit in, but they are absolutely marching to the beat of their own drum.
So, how are we going to crack their code? Well, first, we'll figure out their basic identity. Then, we'll see who gets into the exclusive transition metal club. After that, we dive into the source of their superpowers, these things called unpaired electrons, and see how that makes them masters of connection in things like catalysts and alloys. And finally, we'll investigate a really bizarre atomic anomaly called the lanthanoid squeeze.
Okay, first things first. Before we can get why they're rebels, we've got to know what they are. What exactly gives an element its D-block identity card? Well, it all comes down to where their very last electron decides to call home.
Now, this might sound a little technical, but it's actually a super weird quirk of physics. Imagine you're building an atom, adding electrons to shells like layers of an onion. You fill up the fourth shell, the outer layer, and you'd think you just keep building on that layer, right? But nope. The universe has a strange rule. The very next electron has to go back and fill an empty spot in the third shell, the one just underneath. This inner shell is called the penultimate shell, and if an atom's final, differentiating electron lands there, bam! It gets its D-block identity card.
Now here's where things get really interesting. You might hear the terms D-block and transition metal used like they're the same thing, and a lot of the time they are. But really, there's like a velvet rope and a bouncer. Not every single D-block element gets into the true transition metal club. There's a very strict entry rule.
So here's the bouncer's rule. To get past that velvet rope, your d orbital can't be completely full. It needs at least one empty seat. This applies to the element either in its normal, neutral state, or when it forms one of its common stable ions. If that d orbital is totally packed with electrons in both of those situations, you're out. A full d orbital is an absolute deal breaker.
And this slide shows that rule in action perfectly. Let's put zinc and copper to the test. In their neutral state, they both have a full 3d orbital. So neither one looks like a transition metal yet. But let's check their common ions. When zinc loses 2 electrons to become stable, those electrons come from the outer shell, leaving that inner 3d orbital still completely full. So zinc fails the test. It's in the D block, but it doesn't get into the club. But now look at copper. When it forms its stable ion, it loses 1 electron from the outer shell and 1 from the inner 3d shell, and that leaves it with an incomplete d orbital. That's its ticket in. So copper is both a D-block element and a true transition metal.
So we've established that this incomplete d orbital is the secret handshake. It's the key to the whole thing. But why does it matter so much? Well, it's because this single feature is the source of all their most famous properties. Their superpowers, if you want to call them that. It explains their strength, their amazing colors, their magnetism, everything.
So let's explore that a bit. Have you ever wondered why metals like iron and titanium are so incredibly strong and have such high melting points? Or why a solution of copper sulfate is that brilliant, beautiful blue, but a solution of zinc sulfate is totally colorless? The answer to both of those mysteries is hiding in those partially filled d orbitals.
This chart shows that first superpower perfectly. Think of each unpaired electron as a tiny little anchor an atom can use to hold on to its neighbors. The more anchors you have, the stronger the bond. This chart shows the energy it takes to pull those atoms apart. Chromium, with a ridiculous 6 unpaired electrons, has the strongest bonds by a mile. But look at zinc. It has 0 unpaired electrons, and its bonds are the weakest. This incredible bond strength is why transition metals have such insanely high melting and boiling points.
Okay, now for the color. This isn't just about having unpaired electrons. That's only part 1 of the secret. The second, and really crucial part, is that those electrons have to be able to perform this special little dance move called a d-d transition.
So here's how that little dance works. First, the d orbitals split into 2 different energy levels. Think of a low-energy floor and a high-energy floor. Now, when light shines on the atom, an electron on that lower floor can absorb a specific color of light. Let's say it absorbs the orange light, and it uses that energy to jump up to the higher floor. Now, because that orange light was absorbed, it's missing from the light that reflects back to our eyes. So what we see is whatever is left over, the complementary color, which in this case is blue.
That's why a copper solution looks so vividly blue. And this whole process is only possible if you have an unpaired electron that can make the jump and an empty spot for it to land, the absolute signature of a true transition metal.
This unique electron setup doesn't just give them cool physical properties, it makes them absolute masters of connection. It's the reason for two of their most important jobs in industry, their incredible ability to act as catalysts and to form amazing alloys.
So, why are they such great catalysts? Well, think of a catalyst like a chemical matchmaker. For one, they have a versatile identity. They can easily change their charge, which means they can adapt to interact with all sorts of different molecules. And second, they're experts at temporary bonds. They don't form a permanent, strong bond with the reactants. Instead, they form a short-lived, unstable complex. They just bring the reactants together, give them a little nudge to react, and then let go, totally unchanged. It's the perfect chemical matchmaking service.
And what about alloys, things like steel and brass? Well, to make a good alloy, you need atoms that can mix and mingle without messing up the whole structure. And it just so happens that the atomic sizes of the transition metals are remarkably similar. This means you can easily pluck an iron atom out of its crystal structure and just pop a chromium or nickel atom in its place without causing any problems. This easy substitution is the absolute key to creating strong, stable, and incredibly useful alloys.
All right, for our final secret, we're going to look at one of the weirdest rule-breaking behaviors of them all. We're all taught a simple rule. As you go down a column in the periodic table, the atoms get bigger. You add more electron shells, you get a bigger atom, right? Well, the D block has a major surprise for us.
Just look at this chart. As you'd expect, when we go from the 3D series to the 4D series, the atoms get a lot bigger. Makes sense. But now, look what happens when we go from the 4D series down to the 5D series. The size increase just vanishes. Zirconium in the 4D series and hafnium, right below it in the 5D series, are almost the exact same size. This is not normal. What on earth is going on here?
The culprit has this wild name, the lanthanoid contraction. Here's the deal. Right before you get to the 5D elements, you have to squeeze in 14 electrons into something called the 4f orbital. And these f orbital electrons are terrible at their job. Their job is to shield the outer electrons from the full, powerful pull of the positive nucleus. But because these 4f electrons provide such a poor shield, it's like a shield made of Swiss cheese. The nucleus can reach out with its full force and yank those outer electrons in much more tightly than you'd expect. This inward pull contracts the atom, and it almost perfectly cancels out the size increase you'd normally get from adding a whole new shell.
And this squeeze has huge consequences. First, it creates chemical twins. Because zirconium and hafnium are pretty much the same size, their chemical properties are almost identical. This makes them incredibly difficult to separate from each other when we find them in nature. Second, it leads to extreme density. As you go from the 4D to the 5D series, you're adding way more protons and neutrons, a lot more mass, but the volume is staying the same. More mass in the same space means incredible density. It's why metals like gold and platinum are so unbelievably heavy.
So in the end, after all this, it really does all come back to one thing: their unique electron configurations. That partially filled d orbital, the very thing that makes them rebels, is the source code for their incredible strength, their vibrant colors, their power as catalysts, and even their bizarre defiance of atomic size trends. It is what makes them so challenging, but also so incredibly useful.
Which leaves us with a final thought to chew on. These elements are like nature's ultimate toolkit for building strong, colorful, and highly reactive materials. Given their unique ability to form all these connections and to change their chemical identities on the fly, you just have to wonder, what new catalysts, advanced alloys, or revolutionary technologies will these rebels of the periodic table make possible for us in the future?